Bismillahirrahmanirrahim. Welcome students to the second lecture of Laplace transform. In this lecture we will basically study some properties of Laplace transform and using those properties and we'll just see the some table or a table of Laplace transform pairs. We'll just use these properties and that table to transform from one domain to another domain. So first of all, we'll study about linearity. Linearity is basically superposition of two properties which are additive and homogeneity. What does additive property say? It says that if you have two functions, let's say f1 of t and f2 of t in time domain, and you just add them up in time domain and you want to find out their transform for Laplace transform, all you have to do is that you have to add their Laplace transforms in S domain. So if f1 of t's Laplace transform is f1 of s and f2 of t's Laplace transform is f2 of s, and if they are added at the input, if they are added in time domain and we want to find out their Laplace transform, all we have to do is we have to just add their Laplace transforms f1 of s and f2 of s. Similarly, if f1 of t is multiplied with by any constant a1, so what would the impact in Laplace transform? Only f1 of s would be multiplied with the same constant a1, and that's it. We don't have to do any additional calculations. If we know the transform of f1 of t, we'll just multiply that transform with a1. So this is the property of linearity, whose proper basically definition is given in equation 15.7. So the next property is scaling in time domain. So whenever a constant a, which is positive greater than 0, multiplied with t as shown in 15.10, the overall impact would be as shown in 15.12 equation. Laplace of f of a t is equal to 1 by a f of s by a. So if you know the Laplace transform f of t, all you have to do is you have to multiply that f of s with 1 by a, and you have to replace all the s's with s by a. Wherever you find a s, you have to replace that s with s by a. The next property is shifting in time domain. So whenever a function is shifted in time domain, the overall impact in frequency domain is that an exponent e raised to power minus as is multiplied with that s domain function f of s. So in the equation 15.15 we can see that function f of t is shifted by a. A is a constant and u of t minus a just represents its shift in time domain. So it would be 0 for t less than a, and it would be a u f of t for t greater than a. So after solving this integration, we can see that final answer is that in equation 15.17 we have that e raised to power minus as multiplied with that f of s. The next property is frequency shift. Shift in frequency domain. As in previous slide we have seen the shift in time domain, now we have shift in frequency domain. So shift in frequency domain basically results in multiplication of an exponent e raised to power minus at in time domain. So these are basically frequency translation or frequency shift. Time differentiation. If we differentiate a function f of t, so what would the impact, overall impact in S domain? So we can see that whenever we differentiate a function f of t, so its first differential would result in multiplication of s with f of s and minus f of 0 minus. F of 0 minus is basically initial condition, or you can say value of f at 0. This is the result of first derivative. Similarly, if we have a second derivative or third derivative or fourth derivative, any number of any degree of derivatives we can have. So final equation, which is generalized equation, that is 15.25, which says that the degree of derivatives, we have, let's say n is the degree of derivatives, so we'll have s raised to power n f of s, then there would be s raised to power n minus 1 f of 0 minus s raised to power n minus 2 f derivative 0 minus, and so on. So there would be one major term, that is s raised to power n f of s, and then there would be initial conditions of previous all the derivatives multiplied with s raised to power n minus that degree of derivative, for example n minus 1, n minus 2, and so on. Similarly, time integration basically results in, so time integration basically results in, the final result is that f of s is multiplied by 1 by s. So that is the integration in time domain does to frequency domain in Laplace transform. So in Laplace, whenever a function is integrated from 0 to t, all we have to do in Laplace transform is we have to multiply it with 1 by s. Similarly, the frequency differentiation in frequency domain is basically equivalent to t multiplied with f of t and with a minus sign. This minus sign occurs because of this e raised to power minus st, so we have to use this minus sign on either side of the equation. Time periodicity. Okay, so we will have many periodic functions which will be used to find out their Laplace transform. So whenever we have a periodic function as shown in figure 15.4, we can basically decompose this periodic function into smaller periods. For example, we have decomposed f of t as shown in figure 15.3 into three parts as shown in figure 15.4, and we can call them f1 of t, f2 of t, f3 of t. For any periodic signal, if we can find out its Laplace transform of just one period, and we can just represent it as basically shifted functions of that basic period. So to find out the Laplace transform of any periodic signal, all we need to find is that only Laplace transform of its one period, and that will be called as f1 of s, and we can use equation 15.40 to find out overall Laplace transform of that periodic signal, which would be equal to f1 of s divided by 1 minus e raised to power minus capital Ts. This capital T is basically period of that particular function in time domain. So this is the table of properties of Laplace transform given in book as table 15.1. So all of these properties, their time domain and frequency domain or phasor domain equivalents are given in this table, and this as well. So and vice versa. So example says that obtain the Laplace transform of f of t, which is basically addition of three different functions, delta of t, u of t, and e raised to power minus 2t u of t. So as we have seen the property of linearity, we know that if we know the Laplace transform of delta of t, if we know the Laplace transform of u of t, if we know the Laplace transform of e raised to power minus 2t u of t, we'll just add them up and we'll multiply the Laplace transform of u of t with 2 and multiply Laplace transform of e raised to power minus 2t u of t with minus 3. So that's what we have done in this equation, in this solution. Okay, Laplace of delta of t, as we can see in table 15.1, is 1. Laplace of u of t is 1 by s, which we have multiplied with 2, and Laplace of e raised to power minus 2t u of t is 1 by s plus 2, and we have multiplied this with minus 3. And you can even leave the answer over here, or we can just take the LCM and use this equation s square plus s over 4 over s into s plus 2 as our final answer. In next example, it says that find the Laplace transform of t square sine 2t ut. So basically we have two functions multiplied, sine 2t and t square. U of t is just a function which says that it starts from 0 to infinity. So we already know that from the table we can see that Laplace of sine of 2t is 2 square 2 divided by s square plus omega square. In the table we have omega instead of this 2. So using frequency differentiation, which we have just studied, that Laplace of t square into sine 2t. So t square into sine 2t should be equal to minus 1 square d square over ds square, and inside we'll have the same equation sine of 2t Laplace transform. So we just double derivative of this equation, and using this double derivative we can find the final answer, which is this. Here's another example which is of periodic signal. So as we can see in the figure, the period of this signal is 2. So that capital T is 2. And similarly we have to find out a equation for one period, and for that one period we have to find out its Laplace transform, and then using that equation which we just studied, f1 of s divided by 1 over 1 minus e raised to the minus ts, we can find out the Laplace transform of this periodic signal, which is given at the end of this page. So that's all about the Laplace transform. We have basically studied the basic definition of Laplace transform. Then we have seen the equation, which is 15.1, which is used to find Laplace transforms. Then we studied the properties of Laplace transform, and we have seen the table, which is two tables which are properties of Laplace transform and Laplace transform pairs, which can be used to transform directly from one domain to another domain. In the next lecture, we will study about inverse Laplace transform. How can we just transform a function from S domain, Laplace domain, to time domain using this table 15.2. This will be discussed in detail in next lecture. Till then, Allah Hafiz.